Hi, everybody. Today we begin chapter 2 in our textbook, Electric Circuit Theory, by Nilsson and Rydell. So the topic for today is section 2.1, and we're going to cover the material about dependent and independent voltage and current sources. So we're going to talk specifically or in general about circuit elements. And by the end of this section, you will know some things. We'll talk about the difference between independent and dependent sources. We'll talk a little bit about resistors in 2.2, which will be not on this lecture, but on the following lecture. We'll talk about Ohm's law, Kirchhoff's law, and calculate the power for a circuit. But the topic of today is just section 2.1, understanding independent and dependent sources. So basically, electrical sources convert non-electrical energy to electric energy. And we had talked before about voltage being a separation of charge and current being a movement of charge. So electrical sources that convert non-electrical energy to electric energy include batteries, which are associated with a voltage and convert chemical energy, whether it's a lead acid or a lithium diode battery, that sort of thing. Whatever it is, it stores energy in a chemical form and then converts it to electric energy, or a generator, which converts mechanical energy to electric energy. So we use two ideal models of electric sources. One is an ideal voltage source, and one is an ideal current source. So an ideal voltage source is a theoretical element, which I want to stress this is a theoretical piece of a circuit, but it will supply the same voltage regardless of the current flow. Or an ideal current source, which supplies the same amount of current regardless of a voltage drop. So in real life, a battery might approach an ideal voltage source, and perhaps a circuit controlled with a transistor would be something that would be a constant current source. But it's really important to know, especially if you're familiar with Kirchhoff's law, V equals IR, or the law that we talked about before, that power is equal to voltage times current, that those do not apply on independent sources. They only apply on dependent sources. So in other words, an independent source, which we're going to discuss the difference between these two things in just a moment, but an independent source, whether it's an independent voltage source or an independent current source, will stay the same no matter what. So you can't calculate power, and you can't calculate resistance, or you can't calculate voltage if you're talking about current, an independent current source, or you can't calculate current if you're talking about an independent voltage source. So an ideal independent voltage source is drawn like this. It's a circle with a positive and negative indicating the two terminals. So the circle indicates that it is ideal. So you can use this to determine the voltage of a circuit, but you cannot use it. You can't determine the current flowing across that particular ideal element unless without more information. Let's put it that way. Similarly, if you have an ideal independent current source, it is also indicated with a circle. However, in this particular case, you have an arrow instead of the plus and minus signs. So in other words, we're not talking about this, which is V sub S or voltage, but here we're talking about an I sub S. So that's the difference. They're a little bit confusing because the picture is a circle in either case. So you have to look within the circle to see if we're talking about an independent current source or an independent voltage source. So the observation at the bottom of the slide, if all we have is the current flowing through an ideal current source, there is no formula we can use to calculate the voltage drop. And similarly, if you look at the slide about the voltage source, if all we have is a voltage drop, there is no formula that we can use to calculate the current. And that's sort of indicated by this drawing off to the right. Right. So if we can't use that, when can we use it? Well, if an element is dependent. So we're going to talk a little bit more about the idea of an independent versus a dependent source. So as it says, the sources just presented, they're both represented by circles, are independent because the voltage or current supplied by the source does not depend on any other quantity. It just is. So if you have a battery, until the battery starts to drain down, it will provide, a 9-volt battery will provide 9 volt. Or if you plug something into the wall, it will provide 110 volts, no matter what you plug into it. Now, you may overdrain the power, you may pop the circuit, and may blah, blah, blah. But in general, you're going to be supplied at 110 volts no matter what. So as it says, as you might have already guessed, there are other sources that supply voltage or current whose value is dependent. And since ones that you can't calculate are called independent, the ones that you can calculate are called dependent. So instead of being represented by a circle, they are represented by a diamond shape. And basically, we have to take a minute to look at the variables and the subscripts of the variables. So this is a dependent voltage source. You see it's dependent because it is a triangle, or excuse me, a diamond rather than a circle. And it's voltage because there's a plus and a minus indicating the two sides of the terminal. Over here, we have an equation that says V sub S is equal to some constant mu times V sub X. And that's just relates to what's going on. So this is a voltage controlled source where the V sub S is the voltage supplied and some fraction of it is used, and V sub X is the controlling voltage. So in other words, the V sub X is the independent voltage. Over here, I sub X is the independent, or it doesn't even have to really be independent, but for now, let's just say independent amperage or current. Now, the other thing I want you to see when you look at these, variable or these coefficients, mu and rho, this mu is going to be dimensionless. In other words, its voltage is equal to something times some other voltage. So the units of mu are dimensionless. However, over here we have rho times current is equal to voltage. So this is actually going to be in volts per amp. And so it's a gain, and the units, like it says, are volts over amp. Here, volts over volts, which is dimensionless. All right, similarly here, we have a dependent current source. So we still have the diamond shape, but now we have an arrow indicating this is an independent, or excuse me, a dependent current source. So here we have a voltage controlled current source. So this variable is V sub X multiplied by some constant, in this case alpha, which is equal to I sub S, or the current supplied. So once again, this is going to have, alpha is going to have units of amps per volt. Over here, we have a current, the controlling current, and some constant or so much gain that we have that's going to have a supplied current. So beta here is dimensionless. The units would be amps over amps, so it is dimensionless. And once again, like we talked about in chapter 1, it's really important to keep your units in base units. You'll really not be happy if you try to use milliamps or millivolts or anything like that. Take things to base units in order to operate on these correctly. Okay, so let's take a look at a couple of things here and also talk about what is going on with this delta. I sub delta is just a symbol. So I sub delta, which we're saying is 15 milliamps, 15 times 10 to the minus third amps. How much voltage does this dependent source supply? Okay, so what we're really doing is setting up an equation that says V sub S is equal to 100 times I sub delta. Well, I sub delta is 15 times 10 to the minus third amps. And if you multiply that by 100, you get 15 times 10 to the negative 1, or 1.5 volts. So in other words, this is being controlled by amperage, and yet it is a voltage source. So the 100 is going to have units. That constant of 100 is like a mu or an alpha, and then units are going to be such that it makes out that the controlling amperage results in a volt. So it's really a gain, I guess is what you would say. But you have to be careful when you look at these, because otherwise it looks like you're saying that the amperage is some percentage or some factor of the amperage. And it can be that way if it's an amperage on an amperage controlled circuit. But if it's not, if it's in this case, amp current control, but you're calculating a volt. So the constant just relates to that relationship. Here, what units are associated with a gain of 0.25 for this dependent source? Okay, so if you look at the symbol, this is current, isn't it? Based upon current. So current supplied is equal to 0.25 times the independent current. And so what that tells us is that both are current, so the units are going to be amps over amps or dimensionless. I would argue that A would also be true, but it wouldn't be informative. But volts over volts is dimensionless. It's just that this one is based on current, so amps over amps is a little bit clearer. Okay, we have another one here where we have a voltage supplied and a voltage sub X, and we have a current. So what does that mean? Well, we don't know. We can't tell anything by this because we're looking for something having to do with current, but all we are given are two factors of voltage. And so we do not have a formula to make that calculation. All right, next thing we do is we look at circuit element of interconnected sources. We have a terminal A and a terminal B in each of these cases, terminal A or in terminal B. So what that means is that in this entire circuit, from terminal A to terminal B, or if you think of it the other way, the voltage has to be the same and the amperage has to be the same. So if you take a look at this, here we have 10 volts and 10 volts, both are independent sources. The polarity is the same and the value is the same, so that is a valid circuit. Here on the same two-node circuit, we have a 5 amp and a 2 amp independent source. Those values are different. We have different amperage in the same circuit. That is not valid. So this is just a drawing. This does not have any analogy in real life. What about here on the third one? Well, we have an independent current source, which is, excuse me, an independent voltage source at 10 volts and an independent amp current source, excuse me, I keep saying that wrong, independent voltage source at 10 volts and an independent current source at 5 amps. Is this valid? Yes, it is, because they don't contradict each other. 10 volts, which is that separation of charge, 5 amps, which is the movement of charge, it works in the same circuit between the two nodes. Okay. So if we take a look at this circuit, is this interconnection valid? Well, we have a 5-volt voltage source and we have something going on with our current that is based on that voltage source. There's no contradiction there. And so the answer to that is yes. This one bothers me a little bit. Let's take a look here for just a second. See, this one says that it is not valid. And I think that this drawing is in error. if I look at this, this is the same. The drawing here on this slide is the same, except it says the interconnection here is not valid. I do not see where it is not valid. So if you take a look at this, if you see something different about that I am missing, please let me know. But to me, it looks basically identical to the drawing before, which is valid, and I don't see a reason why this is not a valid interconnection. So I would love to hear differently if you have a different take on that. Okay, here we want to find V sub G. So in other words, we want to find the potential drop or the voltage across this element, which is an independent circle voltage source. We have I sub B flowing here, and here we're told that I sub B over 4 goes through this dependent, and we have 8 amps flowing through the entire circuit. Okay, so the first thing that we see is that I sub B is what's going to flow over V sub G. And so we are told that that is going to be I sub B over 4, okay, because these two are in parallel with each other. I sub B has to be the voltage, the amperage supplied in the circuit, which is 8 amps. It's negative because of the direction of flow. And so V sub G is going to be 8 or negative 8 amps over 4 to give us negative 2 volts. Okay, so we have V sub G, which we substitute in, we get 4 and we get negative 2. What's the power? Well, the power is going to be the voltage times the amperage. And so we do that, we get negative 16 watts. All right, so then the last thing they ask is, if you take a look at the at this, we just discovered that the power associated with the 8 amp source is negative 16 watts. Is this source supplying or absorbing power? Well, let's think about if we're using that passive sign convention, negative power would mean that it's supplying. But what's going on here? Okay, so if we have I sub B as it moves around the circuit, and we are looking at it flowing on the battery from positive to negative, which is a supply. The natural flow, I guess, would say, I don't know if that's accurate to say, but I think of it as being a natural flow from negative to positive means it's absorbing. If it's going positive to negative, then it is supplying. All right, and that's the first part of this chapter that covers section 2.1. Our next lecture will cover section 2.2 and 2.3, where we'll start talking about Ohm's law. But right now, the two things I'd like you to think about are the difference between an independent source and a dependent source, and also, of course, continue thinking about that passive sign convention. As far as elements that may be confusing, make sure to look at the element, whether it's an independent or dependent element. If it has plus minus, it indicates that's voltage. If it has an arrow, that indicates it's amperage. And finally, remember that on an independent element, on an independent source, you cannot use the standard equations to make calculations, because that voltage or that current is going to be constant throughout the cycle, throughout the circuit, no matter what. And so on the other elements, you can make those calculations, but not on the independent elements. All right, well, I will post some homework for this along with this video. And then when you do turn in your homework, do not turn in the homework for section 2.1. You'll turn in all of the homework for chapter 2, which will be 2 or 3, I think 3 videos and 3 homework assignments, but it will all be listed underneath the homework assignment for chapter 2, and turn it in all at the same time instead of turning it in one piece at a time. Turn in all of chapter 2 homework at the same time. All right, have a wonderful day, and we'll talk to you later.